Astronomers pointed two of the most powerful telescopes ever built at the same tiny patch of sky, combined their data, and found something that, according to the researchers themselves, simply shouldn't exist yet. Not a single galaxy. An entire cluster of them, 66 separate galaxies bound together by gravity, wrapped in a cloud of gas hot enough to glow in X-rays, sitting at a point in cosmic history when the universe was supposedly still far too young to have built anything this massive. The lead scientist behind the discovery put it about as plainly as a researcher ever put something like this. The universe, in his own words, was in a huge hurry to grow up. This is the real story of JD's ID1, the most distant galaxy protocluster ever confirmed, how two completely different telescopes had to work together to find it, and why its sheer size at such an early point in cosmic history is forcing scientists to reconsider how quickly the universe's largest structures were actually capable of forming. If you want more real discoveries explained without the exaggeration, subscribe now, because this particular puzzle is still very much unresolved. It helps to understand where this discovery actually came from within Webb's broader observing program, because JD's ID1 wasn't found through a single, isolated observation. The galaxies making up this protocluster were originally cataloged as part of the JWST Advanced Deep Extragalactic Survey, commonly known as JADES, an ongoing large-scale observing program specifically designed to systematically hunt for and characterize the earliest galaxies in the observable universe. That program has already been directly responsible for identifying some of the most distant individual galaxies ever confirmed, and JD's ID1 represents a different kind of result entirely, not a single record-breaking galaxy, but a systematic search through the accumulated catalog, specifically looking for regions where multiple distant galaxies appeared to be clustered unusually close together on the sky, a pattern that can indicate a genuine physical grouping, rather than galaxies that simply happen to appear near each other from Earth's specific vantage point, without actually being physically associated at all. To understand why finding this specific object matters so much, you first have to understand what a protocluster actually is, because it's a genuinely different kind of object than the individual distant galaxies that usually make headlines. A galaxy cluster, in the modern and nearby universe, is a vast collection of anywhere from hundreds to thousands of individual galaxies, all bound together by their combined gravity, representing some of the largest structures the universe has ever assembled. A protocluster is essentially that same kind of structure caught in its infancy, a region where a large number of young galaxies are actively in the process of being pulled together by gravity, still embedded within a surrounding cloud of hot gas, not yet fully matured into the kind of tightly bound, clearly defined cluster astronomers see much closer to home. Finding a protocluster is considerably harder than finding an individual distant galaxy, precisely because the galaxies inside one aren't yet tightly bound together, and the surrounding gas that usually makes mature clusters easy to spot in X-ray light typically isn't developed enough yet to be reliably detectable. It's worth spending a bit more time on Chandra specifically, because its contribution to this discovery represents a genuinely different kind of astronomy than the infrared imaging most people associate with Webb. Launched by NASA back in 1999, the Chandra X-ray Observatory was specifically designed to detect X-ray radiation, a form of light with far higher energy than anything visible to the human eye or captured by Webb's infrared cameras, produced by only the hottest, most energetic processes in the universe, material heated to millions of degrees, whether by falling into a black hole, being shocked by a supernova explosion, or, in this specific case, being compressed and heated as an enormous cloud of gas collapses under its own gravity within a forming protocluster. Webb and Chandra essentially see completely different aspects of the same underlying object. Webb picking out the individual points of light representing each distant galaxy, and Chandra revealing the invisible, superheated gas woven throughout and around them, providing independent confirmation of the actual gravitational mass holding the whole structure together. Neither telescope alone could have confirmed JD's ID1 with the same level of confidence. It took both, observing the same tiny patch of sky in two completely different ways, to build a genuinely convincing case that this collection of 66 galaxies represents a real, physically bound structure rather than a coincidental alignment. That specific difficulty is exactly why finding JD's ID1 required combining two entirely different telescopes rather than relying on either one alone. A research team led by Akos Bogdan of the Harvard and Smithsonian Center for Astrophysics used the James Webb Space Telescope's infrared instruments to identify the actual galaxies making up the structure, ultimately detecting at least 66 separate galaxies held together by gravity within a single compact region of sky. Separately, the team turned to NASA's Chandra X-ray Observatory, a telescope specifically built to detect X-ray emissions rather than visible or infrared light, and found that the region surrounding those galaxies was giving off exactly the kind of X-ray signal produced by an enormous cloud of superheated gas. That X-ray detection mattered enormously for confirming the discovery, because it meant the structure had already accumulated enough combined mass to heat its surrounding gas to extreme temperatures, providing independent physical evidence that these 66 galaxies weren't simply sitting near each other by chance, but were genuinely bound together as a single, massive, gravitationally coherent structure. If a story built on real, peer-reviewed research published in Nature is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. To really appreciate the scale involved here, it helps to compare JD's ID1 to a fully matured galaxy cluster much closer to home. The Coma cluster, one of the most well-studied galaxy clusters in the nearby universe, contains somewhere in the range of 1,000 or more galaxies, all tightly bound together and easily visible as a distinct, dense structure in the night sky roughly 320 million light-years from Earth, a cluster that took the better part of the universe's entire history to fully assemble into its current, mature state. JD's ID1, by comparison, had already gathered 66 galaxies and 20 trillion solar masses together into a single gravitationally bound structure after only about 1 billion years, a small fraction of the time a cluster like Coma had available to reach its own considerably larger, more mature state. That comparison helps illustrate exactly why researchers describe JD's ID1's existence as such a genuine puzzle. It isn't simply an early galaxy cluster behaving the way theory expects an early-stage structure to behave. It's a structure that appears to be running dramatically ahead of the developmental schedule every existing model has assumed large-scale cosmic structures actually follow. Here's where the numbers involved start to become genuinely difficult to reconcile with existing theory. JD's ID1 sits roughly 7 billion light-years from Earth, meaning astronomers are observing it as it existed when the universe itself was only about 1 billion years old, a small fraction of its current age of roughly 13.8 billion years. Despite existing at that extraordinarily early point in cosmic history, the structure has already accumulated an estimated mass equivalent to 20 trillion suns and spans a staggering 1.1 million light-years across, a scale that dwarfs the size of any single galaxy, including our own Milky Way, by an enormous margin. According to the research team's own analysis, most existing models of how the universe's largest structures form predict that a protocluster this massive shouldn't have been able to come together until somewhere between 2 and 3 billion years after the Big Bang. JD's ID1 appears to have already reached this scale after only about 1 billion years, arriving on the scene 1 to 2 billion years earlier than current theoretical models say should be possible. Akos Bogdan, the study's lead author, addressed that specific discrepancy directly in the statement accompanying the discovery's publication. He described JD's ID1 as potentially the most distant confirmed protocluster ever seen, and stated plainly that the structure is giving astronomers new evidence that the universe was, in his own words, in a huge hurry to grow up. That phrase captures the core tension driving the entire discovery. Building a structure containing 66 gravitationally bound galaxies, spanning over 1 million light-years and massive enough to heat surrounding gas into detectable X-ray emission, is supposed to require considerably more time than the universe had actually had available when this particular light left its source. If you found this as genuinely puzzling as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. To understand exactly what existing theory predicts should happen instead, it helps to walk through the basic process. Cosmologists call hierarchical structure formation, the framework underlying essentially all modern predictions about how galaxies and galaxy clusters assemble over cosmic time. In this picture, the universe's very first structures were small, individual clumps of matter, gathering together under gravity in the aftermath of the Big Bang. Those small clumps merged with neighboring clumps to form the first small galaxies, which then continued merging with other nearby galaxies over enormous stretches of time, gradually building up larger and larger structures, eventually assembling into the massive galaxy clusters seen throughout the nearby universe today. Each step in that hierarchy is expected to take a substantial amount of cosmic time, which is precisely why models predict that a protocluster on the scale of JD's ID1 shouldn't be able to complete this entire layered merging process until 2 to 3 billion years after the Big Bang at the earliest. Finding a structure of this exact scale at only about 1 billion years suggests that either individual steps in that hierarchical process happened considerably faster than expected, or that the universe's very earliest matter distribution was already lumpier, already further along than the smooth, gradually clumping picture standard theory currently assumes. It's worth understanding why the timeline problem here is specifically difficult to explain away, rather than simply being a minor rounding error in an otherwise solid theoretical framework. Building a structure on this scale requires gravity to pull together an enormous amount of matter across a genuinely vast region of space, a process that, according to the standard model of cosmology, often called lambda CDM, should unfold gradually over billions of years, as smaller clumps of matter merge into progressively larger ones. Finding a structure of this exact scale existing after only about 1 billion years means either that matter clumped together and merged considerably faster than existing simulations predict, or that the underlying distribution of matter in the extremely early universe was somehow less uniform, more clumpy from the very start than current models assume, giving gravity a considerable head start it isn't currently thought to have had. Neither explanation is a small tweak. Both would require real, substantive revisions to specific assumptions baked into how astronomers currently model the growth of the universe's largest structures. There's also a connection here worth drawing to a completely different, equally fundamental open question in cosmology, the distribution and behavior of a dark matter throughout the early universe. Galaxy clusters and protoclusters don't actually form primarily because of the gravity of the visible matter. Astronomers can directly observe stars, gas, and galaxies. They form because that visible matter is embedded within enormous invisible concentrations of dark matter, which provides the overwhelming majority of the actual gravitational pull driving structures like JD's ID1 to assemble in the first place. A protocluster forming dramatically earlier and faster than expected could imply that the underlying dark matter distribution in the extremely early universe was already more clustered, more unevenly distributed than current models assume, an idea that connects directly to the same broader category of open questions researchers have been grappling with across essentially every unusually early, unusually massive structure Webb has helped identify so far. Untangling exactly how much of JD's ID1's surprising timeline traces back to dark matter behavior specifically, versus other factors like unusually efficient star formation within the individual galaxies themselves, remains an active area of ongoing research that scientists studying this discovery have specifically flagged as a priority for follow-up work. It's also worth situating JD's ID1 within the broader pattern of similarly unsettling discoveries Webb has produced since it began operating, because this protocluster isn't an isolated anomaly showing up out of nowhere. Separate research efforts have identified individual galaxies existing within the first few 100 million years of cosmic history that appear far more massive and chemically developed than models predicted they should be, along with an entire population of unusually bright, unusually early galaxies and a distinct population of small, compact objects called little red dots, several of which have turned out to be actively feeding black holes with masses that don't comfortably fit existing models of how black holes are supposed to grow this early in cosmic history. JD's ID1 adds an entirely different kind of evidence to that same growing body of findings. Not an unusually massive individual galaxy or an unusually large black hole, but an unusually massive collection of galaxies, already assembling into the kind of large-scale structure current theory says needed considerably more time to take shape. Astronomers studying the discovery have been direct that the natural next question, exactly how a structure this size managed to assemble so quickly, remains genuinely open. According to current models, researchers have noted there simply wouldn't have been enough time, or enough already formed galaxies available in the first billion years of the universe's history, for a protocluster of this specific size to come together through the gradual hierarchical merging process standard theory describes. That leaves researchers with a real unresolved puzzle rather than a tidy, already understood explanation. Precisely the kind of situation that tends to drive follow-up observations and continued theoretical work rather than a quick, settled answer. It's important to be clear about what a discovery like this does and doesn't mean for our broader understanding of the universe, because responsible reporting requires holding both sides of that distinction honestly. Finding a protocluster too large and too early for current models doesn't mean the broader framework describing the Big Bang and the general expansion of the universe is wrong. That broader picture remains extremely well supported by an enormous range of independent evidence gathered over decades. What discoveries like JD's ID1 actually expose is a specific, genuine tension in one particular corner of that broader framework. Exactly how quickly gravity was able to assemble the universe's large structures in its earliest few 100 million to 1 billion years, a question that, until Webb and Chandra combined their observing power on this exact patch of sky, astronomers simply didn't have the tools to investigate directly at this level of detail. So what does all of this actually add up to? Combining the James Webb Space Telescope's infrared vision with the Chandra X-ray Observatory's ability to detect superheated gas, astronomers confirm the existence of a genuinely massive protocluster, 66 galaxies, 20 trillion solar masses, spanning over 1 million light-years, sitting at a point in cosmic history when the universe was only about 1 billion years old, roughly 1 to 2 billion years earlier than existing models say a structure this size should have been able to form. That finding adds yet another independent thread to a rapidly growing body of evidence, suggesting the earliest chapters of the universe's history were considerably more active, more developed, and more efficient at building large-scale structure than decades of theoretical modeling had prepared astronomers to expect. There's a genuine sense of anticipation running through how researchers have talked about this discovery, rather than simple confusion or alarm, and it's worth ending on that note specifically. A structure like JD's ID1 isn't a problem for astronomy to apologize for or explain away quietly. It's exactly the kind of concrete, well-documented anomaly that tends to drive real scientific progress forward, giving researchers a specific, measurable target to test new ideas against, whether that eventually means refining how quickly gas collapses into stars in the early universe, revising assumptions about the early distribution of dark matter, or something researchers haven't fully considered yet. As Bogdan himself put it, the universe appears to have been in a genuine hurry to grow up, and scientists are still working out exactly how it managed to move that fast. If stories like this, grounded entirely in real, published research instead of exaggerated headlines, are what you come here for, subscribe to this channel and turn on notifications, because Webb and Chandra are both still watching the earliest reaches of the observable universe, and there's a very real chance the next discovery pushes this particular mystery even further. Thanks for watching, and I'll see you in the next one.